Good afternoon and welcome everybody to today's DOE Solar Decathlon webinar, Solar 101, How Solar Energy Works. We'll be getting started in just a few minutes to give attendees more time to join. So hang tight and we'll be right back. Thank you.
Welcome, and thank you for participating in today's edition of the Department of Energy's Solar Decathlon webinar series, which will address Solar 101, How Solar Energy Works. My name is Jonathan Cohen, and I run the Solar Decathlon webinar series with your Department of Energy. First, let me share what the Solar Decathlon is. It is a collegiate competition that consists of 10 contests which challenge student teams to design and build highly efficient and innovative buildings powered by renewable energy. The competition features a design challenge and a build challenge. The Solar Decathlon provides a hands-on experience and unique training that prepares the competing students to enter the clean energy workforce. But the Solar Decathlon is more than a competition. It's an intensive learning experience for the general public and homeowners as they experience the latest technologies and materials in energy-efficient design, clean energy technologies, smart home solutions, water conservation measures, electric vehicles, and high-performance buildings. Participation since the first Solar Decathlon was held in 2002 has involved more than 465 collegiate teams and more than 23,000 collegiate participants from more than 23 countries. These webinars are a learning experience for the public and homeowners as you experience the latest as you experience these things. And so we really want you to ask the questions that you want answers to on today's webinar. I also want to share that recordings of these webinars will be posted afterward. Just go to the website solardecathlon.gov to find them, along with a wealth of resources about the Solar Decathlon. So next slide, please. And we also want you to know about what is going on with the entire series of Solar Decathlon webinars, or in this case, what we call virtual sessions. So they're monthly, and they will run through May. And we have Discovering Clean Energy Careers next month on October 14th at this time. And then a virtual hands-on energy workshop for families in November. We'll have the Solar Student Leaders of Tomorrow Showcase in December. Resilient Home 411, Strategies to Weather and Recover from Natural Disasters in January. Zero Energy Ready Homes, New and Growing Fast in February. The Future of Solar, a tour of cutting-edge solar research with the U.S. Department of Energy in March. The Solar Decathlon Build Challenge Team House Tour in April, when that competition will culminate. And then the Winning Solar Home, the DOE Solar Decathlon Build Challenge winners in May. Next slide, please. So we have a very full slate for you throughout the year. We also like to show you where you are. We have people from all across the country, and it is really quite impressive, a really great geographic distribution. And so thank you, all of you, wherever you are across this great country, to register for today's session. Next slide, please. So we want to engage you in this virtual session. And so we're going to ask you to take a quick poll and share with us which best describes your role or occupation. Please select one of the following: student, homeowner, solar professional, energy efficiency professional, or other, in which case you could chat in to the questions box what you mean. We will cue our voting music and come back with the results in real time. Okay, I think everybody's had enough time to vote. Let's see what the results are, and they are in. And we have quite a spread here. 34% are other. Tyler, you'll have to share what has been chatted in through the chat. 27% are students, 23% are energy efficiency professionals, 10% are homeowners, and 5% are solar professionals. So quite an array. Thank you all for voting. And we'll move on to our next slide. And and we'll see if there is anything coming through in the chat while we wait to move to our next slide. Tyler, anything that you've seen in terms of the significant number of people who voted other?
Yeah, continuation of the diverse nature of the responses. We have an educator, two educators, several architects, a student, and a DOE biologist, among others.
Wow, that is quite a spread. Thank you very much for that, Tyler. And thank you, everybody, for voting in that poll. And so it looks like we are now primed to introduce our first speaker. I think, Tyler, might be one ahead in the slides. So if we can go back a little bit. There we go. We like to review an agenda so you know what's coming up. We'll have three great speakers from the U.S. Department of Energy's solar office today, and they will each cover the different items outlined on the slide on your screen. And we are very fortunate to have this brain trust with us, and also very much appreciative of them as valued colleagues, as normally in usual times they would be down the hall from the office in which I work, although we are all remote, of course, today. So with that, I'm going to introduce our first speaker, and then we're going to get right into it. So Brian Bobb joined the Department of Energy's solar office in 2015 and works as a technology manager within the photovoltaics program, also known as PV. He currently supports program development toward advancing the cost effectiveness of PV modules and systems as an increasingly significant part of the national energy portfolio. Brian holds a BA in physics from Harvard University and a PhD in materials science and engineering from the University of California at Los Angeles. So we are very pleased to turn things over to Brian to be our first speaker today. Brian, the floor is yours.
Thanks, Jonathan. Tyler, would you mind going back up to the pie chart, a couple slides up? Yeah, thanks. I was hoping to start things off with one of my favorite statistics, which is this is the new electrical generation capacity that the world added in 2019. So that's new power plants built and brought online, minus any old power plants that are being decommissioned or taken offline for other reasons. And if you break things out this way, you can see that in 2019, the world added about 244 gigawatts of electrical generation capacity, something like 70 or a little more than 70% of which was renewable, and a huge, healthy 40% or so of actually being solar. So, if there was any doubt that solar energy and wind energy and other renewables were ready for the mainstream or ready to make up a significant part of our electrical grid, it's sort of statistics like this that show that the world has realized that these are very, very legitimate and very abundant ways to generate electricity, and they're actually cost effective enough that they can be deployed on a very large scale now. All right, so next slide, please. All right, the challenge to deploying solar on a very large scale, particularly in this world where we have a lot of it is covered in built environment and used land for other reasons, is how we can integrate solar panels into every part of our lives, all of our buildings, and our various land uses. So solar panels they're great neighbors, in my opinion. They don't make a lot of noise, they don't move around a lot, they don't really bother anybody. So you can actually have them quite close to people, and everything more or less works out fine. The tricky part is integrating them in a way that people actually want them there. They want them to be near them, want to see them all the time. So really, we need a good set of talented architects and designers and developers that have the talent and the experience and the know-how to integrate solar into our buildings, into our farmland, our reservoirs. You can put them all over the place, and they really work great in a lot of situations. So I'm very pleased to be talking to this audience that may actually make up a significant part of the future of the people who will be deploying solar energy or other energy efficiency and energy generation technologies across the country. Next slide, please. So the Solar Energy Technologies Office, where Dave and Kyle and I work, is part of the Department of Energy. Our mission is to make solar affordable and reliable, and also make it a good part of the electrical grid and a good partner to all of the other electrical generation technologies that we use to power our lives. We normally do this by launching lots of exciting research and development and technology development programs, and doing a lot of great work to kind of break down any barriers that are impeding the industry or otherwise causing difficulty for the deployment of solar. Today, we're going to be taking a step back slightly and talk a little more about the fundamentals or the basics of solar energy. What is it? How does it work? What are the various components of solar energy systems? All right, next slide, please. Great, all right, yeah, so I'll be doing the first segment. When you think of a solar energy system, starting at the very basics, there's really three parts. So there's the PV modules themselves, the photovoltaic modules. There's racking and wiring that supports the PV modules and keeps them pointed in the right direction towards the sun, ideally. And there's power electronics that take the electrical energy that's generated and put it onto the electrical grid into a way that it's compatible with all of the other electrical generation technologies that are currently working. If you advance one more. Yeah, so the first segment of this is based primarily on the PV modules, what they're made of, and of course the PV cells that really power the modules and do the heavy lifting here. All right, next slide, please. Thanks. So if you were to take apart a PV module, a photovoltaic module, you'd find generally these main layers. So the frame and the junction box are maybe the odd pieces out here. But anyway, the frame is added to give some additional mechanical support and to make it easier to carry. The junction box allows you to get electrical access to the cells. And other than that, it's basically a sandwich of encapsulation layers and the cells themselves. So the front is generally glass. It's got to be very hard, very tough, able to withstand hail and rain and snow and anything the world is going to throw at them. The encapsulation layers that sandwich the cells, they're a little softer, kind of squishy, maybe designed to give a little bit of pillow and support to the cells and allow them to flex a little bit. The back cover tends to be plastic, although it can also be glass. And that depends on exactly what you're going to want to use your module for and where you're going to put it. And then, can you advance one more? Yeah, and then in the middle is where the magic happens, the solar cells that actually generate the electrical energy that we're going to be harvesting and using as power. Next slide, please. All right, so zooming in on the solar cells that go in the center of the module there, you can see them as the square or slightly off square black or dark shapes in the solar module, as you can see in the image on the left. The central image is kind of a cartoon schematic of a cross section of a solar cell. And there's three main parts that I want to draw your attention to. The first is the absorber. So that's the thick gray rectangle. That is where the light gets absorbed and hopefully generates lots of excited electrons. We need those electrons to create our energy and to harvest our energy from the solar cell. The other two main components of the solar cell are the junction and contacts. And so their job is kind of to act as gatekeepers. They need to push the electrons in the same direction. We need them all moving one way and we need them piling up at one side of the solar cell. Can you advance once? Great, so we shine light on the absorber. The process for energy generation works something like this. So light shines on the absorber and it generates excited electrons. We usually use silicon as the absorber. When you have these kind of dark rectangles in your solar module, you can bet those are silicon wafers. So they're very good at absorbing sunlight. And our goal is to have them create as many excited electrons as possible when they absorb that sunlight. Can you advance one more? All right, and now if we've done our job right and we've designed the solar cell well, the junction and contacts are basically going to force the electrons to congregate, in this case at the top of the solar cell. And as they do, as they all move up there, they're going to leave behind empty spots and positive charge because we just moved a bunch of negative charge with the electrons up towards the top of the solar cell. So there'll now be positive charge near the bottom. That was once balanced by the electrons, but no longer is. And now we have kind of a positive and negative terminal to our solar cell. So if we actually plug wires into the solar cell, we can harvest current and voltage that's based on having all these electrons piled up on one side and all this positive charge piled up on the other side. And so that lets us get electrical energy based on the current and voltage of the solar cell. So that was a very quick introduction to solar cells. There's of course a very large field of science dedicated to making the best possible absorbers that are able to create the most possible excited electrons, and also how to make the best possible junction and contacts that will give us the best power harvesting capability from those excited electrons. All right, next slide. All right, so now if we have some well-performing cells, remember we have kind of the positive terminal on the top, negative terminal on the bottom, or vice versa, depending on how you design your cell. So what we're going to be doing is stringing these cells together so that the top of one cell touches the bottom of the neighboring cell. As you can see in the figure on the left, the cartoon on the left. And so that basically is going to add our voltage together, kind of like if you were stringing batteries together, except solar cells only work when you shine light on them. And so we string these cells together into long rows. They're all strung together in series. And I've kind of added in the middle, the arrows indicate roughly how the current would flow through a solar module as we string these cells together into one long circuit that actually extends through the entire width of the module. One thing to note here is that since all the cells are being strung together in series, if you were to disrupt one of these cells for any reason, it could be hail damage, it could be some other kind of damage, or it could be, as you see on the right, a funny shaped shadow. It happens to get draped across your solar module. You can actually disrupt a lot more cells than you would expect, just because they're all strung together in series, and if one of them gets disrupted, it will have a tendency to block current of the entire string. And so solar modules usually have some fail-safes built in. There's usually 3 separate independent cell strings inside of the solar modules that come together at the junction box. But in any case, I do want to warn everyone that take shading seriously. If a small shadow goes across a few cells, it can actually have an outsized impact on the total ability of the module to generate power. Great. All right, next slide. All right, so when you're deciding what kind of solar panel to use, there's a fair number of options these days. It used to be that only the 2 figures in the top left were kind of available on a wide scale. That's the conventional, generally blue solar modules. And then the high performance ones were kind of the top market, usually carried a price premium. Those are usually a little more black, kind of indicating that they're doing a slightly better job of absorbing as much light as possible. Now we've also got a lot of bifacial modules on the scene, which is exciting. They can actually harvest light from both sides. So if you shine light on the top, it will generate electricity, also light on the bottom. They also have a slightly different appearance. They're generally a little bit transparent. They let light filter through the cells, so you can actually use them in some different applications and create kind of a cool visual effect. But if you're deploying them in the middle of a large field, they'll just have the advantage of being able to collect light that's reflected off the ground and hits the rear side of the solar module. Also, in the last couple of years, a few companies have launched roof tiles, which is exciting because they really offer a lot of variety in terms of where you can deploy them and how they can blend in with their environment. So there's a few examples of these on the market right now. They can either look like you see in these images on the bottom, where you can tell which roof tiles are the PV module or the PV cells. And they also sometimes will be integrated into the roof so fully that it's really actually hard to tell where the PV system is and where the roof begins. So they have full roof tiles like on the left bottom, or just sort of a low profile system where the PV modules are integrated into the roof a little bit lower than usual. So they look very sleek and don't stick up like the normal racking would require. There's also a variety of lightweight and flexible modules available. These are mainly if you want to have a portable application where you want to carry the module around, or if your roof cannot support a lot of weight for any reason. You can sometimes get away with using a lightweight or flexible module that's actually just stuck right onto the roof and doesn't add a lot of weight. In the top right, there are a few companies now that are experimenting with making different color solar modules. Now this does cost a little bit of energy, since the solar module has to reflect a little bit of light in order to be a certain color. But it is quite cool what you can do if you have access to different colored solar modules, and you can even create different textures or images on the solar modules to really personalize your PV system. Right, so that's a quick overview. There's a fair amount of variety out there. So choosing the right one, could you advance the slide, please? Right, and when it comes to choosing the right PV module for you, of course, performance and how many watts it can generate is going to be important. Physical dimensions, how large it is, and also how heavy it is, are going to be important. How much it costs will be important to anyone who's hoping to save money on their electrical bill, which is most people. And also what it looks like, as you saw on the last slide. I wanted in particular to emphasize reliability at the end. So PV modules really go through a lot. You can kind of imagine what it would be like to try to stand outdoors for 20 or 25 years. It's not an easy thing to do. And we asked them to survive rain and hail and snow and high winds and extreme heat. And so they really need to be built well. And they are, for the most part, built very well. And are stress tested to see if they can actually survive these kinds of events. But you do have to be careful and make sure you're getting a well-built solar module from a reputable supplier. Next slide, please. Right, so if you're interested to learn more about any particular PV module, basically the good place to start is the data sheet or specification sheets that are available online. Pretty much every PV module technology will have one of these. It's usually on the website of their manufacturer, and they have lots and lots of information. So modules go through strict qualification and certification programs to make sure that they're going to be able to stand up to life outdoors. And so there'll be many, many tests. Usually some of the information that you get from these tests will be part of the specification sheet too. You can also find exactly how many watts you can expect it to generate, what its weight is, what its dimensions are, what kinds of racking hardware or power electronics might be good to choose for that module, and the warranty, which is always a good thing to know. So regarding warranties, it's almost impossible to predict just how long a PV module is going to last in the field. So the warranty gives you a certain amount of certainty. Be it 25 years or 30 or 35 years occasionally. The trick to actually being able to execute the warranty is you need the company that's providing it to still be there in that time. So picking a reputable supplier is also important if you're going to be relying on their warranty in the future. Great, so I think we've actually made it to the end of the PV cell and module segment. I think now I'll turn things over to Dave.
Great. Thank you very much, Brian. We really appreciate that presentation. We'll ask everybody to think of your questions that you might have based on that presentation and hold on to them, as we will take questions at the end after the third speaker. But now we're going to switch over to our second speaker, and I'm very pleased to introduce David Walter, who is a technology manager for the Department of Energy's Solar Office's System Integration Team. Prior to DOE, David worked in the insurance industry providing field evaluations of solar and wind installations. David is a licensed professional engineer and project management professional and holds a BS in ocean engineering from the United States Naval Academy, having served in the U.S. Navy on submarines as an assistant engineer. And with that, we're very pleased to turn the floor over to David. David, over to you.
Thank you, Jonathan. So I'm going to go through some of the differences between residential, commercial, and utility scale systems. And all throughout the discussion, we'll go through different aspects of the system design and how things you should think about when you're trying to maximize that system performance. We'll also go through a little bit more about the different ways to mount modules to the racking and different solutions for different geographic areas, and go into a little more detail on the shading stuff that Ryan talked about. After that, we'll go through a little bit about how an inverter works, because the panels generate what's called a direct current voltage. So it doesn't vary at all, but like many of you probably know, the voltage that comes out of your wall socket and what the grid uses is what's known as alternating current. So we need to be able to go from that direct current to that alternating current on the grid. And then I'll touch a little bit about the increased use of solar in storage and how it can be used for resiliency. Next slide, please. So the sizing of systems is generally broken down into three different categories in the industry. So there's residential systems, which tend to be about less than 10 kilowatts. The commercial side, that 10 kilowatt to 1 megawatt range. And these are mainly for rooftop, those large scale rooftop type systems. There are some warehouses actually that are even larger than that 1 megawatt. There's two and 3 megawatt size systems out there if they have a lot of area, but they're still thrown into that commercial space because they're connected behind the meter and in how the National Electric Code looks at these things. And then utility scale is generally larger than 1 megawatt, but these are those large ground-mounted systems, which we'll go into a little more detail. A couple other points I wanted to bring up about the differences between these and some of the design aspects are, in a residential system, the National Electric Code only allows you to go up to 600 volts in your panels. So that kind of limits the number of panels you can put together in one of those strings. So you definitely do multiple strings, but the higher voltages we can go to, the more efficient it can be, but there are some safety concerns about that. So that's why residential systems are limited to 600 volts. Commercial systems, however, and multi-tenant buildings are allowed to go up to 1,000 volts. So there's a different class of modules that they can use for that. And utility systems can even go up to 1,500 volts. Another thing about looking at when you're designing the system as a whole, in residential systems, you're kind of limited to what the roof pitch is already on the house and the orientation of the house is, which we'll go in a little more detail about why you want to pick the direction that you point the panels. But like I said, in the residential sector, you're kind of limited in terms of what the house presents to you. Those commercial systems tend to be on flat top roofs, which gives you a little more flexibility, but you also want to minimize the amount of shading between each one of the panels. So they tend to just lay them flat or close to flat so they can maximize the number of panels that can fit on a roof. Whereas in those utility systems, when there's a lot more land area to be used, it allows you to spread the panels out a little bit more and orient them so that they're maximum efficiency. Next slide, please. Okay. And now I'm going to go into a little bit more detail on the different types of racking mechanisms and a little bit more about tracking as well. So next slide, please. So in terms of roof-mounted systems, there's really two main ways to mount them. So in residential systems and a lot of commercial systems, that picture on the left shows how panels are anchored to the roof, because there's a lot of wind that can pick up these panels like a sail, right? So you need to make sure that they're properly secured. And the easiest way one of the ways to do that is to anchor it to the roof system. That can provide potential water intrusion aspects. So it's what we need to do for high-pitched roofs and a lot of low-pitched roofs. But if you look on the right, there's also what's known as ballasted systems, which for in a commercial setting where they can place a lot more weight on their roof, they actually lay these racking systems down and then put large weight. Those black sections are concrete weights that are put in there to just hold everything down. So, next slide, please. And then in terms of ground-mounted systems, there's two main categories on this. There's fixed tilt systems, which are pylons driven into the ground, and then they mount the panels at one specific angle and one specific orientation, typically just facing south, and there's no place for them to move. And then on the right-hand side, that's what's called a single-axis tracker, which allows those panels to basically follow the sun as it tracks through the sky. Next slide, please. And I'll talk a little bit more about the tracking systems and why that is. So if you look at the graph on the top, that shows how the sun moves throughout the sky at 30 degrees north latitude. So if you go further south towards the equator, the distance between the red line and the blue line, they come closer together. The further north you go, those lines spread further apart. So when you're mounting a system, and if it's fixed tilt, you want to basically mount it in the middle so that you're maximizing the amount of energy that you can get throughout all seasons. But a tracking system allows you, in a single axis system, allows you to go follow it from east to west. And a dual axis system, which are more used in those northern latitudes, allow you to change it when it's in the wintertime. You can point the panels close to the horizon, and in the summer move them closer to the apex where the sun is. And that allows you effectively to harvest more energy at the earlier part and the end part of the day, which can translate into a lot more energy harvested, and it's a cost-benefit ratio based on the amount of cost you put into those trackers versus not. Next slide, please. And like I said, just want to give you a couple pictures of single-axis trackers, which a lot of utility systems nowadays are going in, since the cost of those tracking systems have been reduced, or single-axis tracking. And then those dual-axis trackers, they tend to be mounted just in single packages on pylons because they have to be able to tilt north, south, and up and down. Next slide. And now I'll go into a little bit more detail about some of the shading concerns that Brian alluded to. So if you look at the graph on the left, that shaded module, that module is fully shaded. But if you shade one module within a string, it'll bring down the amount of energy that can be harvested from that entire string by up to 40%. And so that's why it's very important when mounting on a rooftop system or out in utility space to look at what the surrounding topology is and your tree cover, so that you can minimize those small shading peaks. Because not only does it reduce the amount of energy comes out of that string, but if you look at the graph on the right, the black line follows what the maximum amount of power is that you can get out of this system based on the voltage. And normally, which I'll talk about in the next slide, the inverters will convert, when they're converting that DC to AC, they want to they're finding the right voltage to operate at to maximize the amount of power it comes out. But if there's a shaded section and we get these two peaks there, it's potential for the inverter to fall into the wrong peak. So it won't actually be maximizing the amount of power. It'll be in that local max where it's generating even less power than it could for the entire system. Next slide, please. So as I just mentioned about inverters, we're going to go in a little more detail about what those, they're also known as power electronics. They do quite a few different things. So the photo on the left are string inverters, and the photo on the right, we'll talk a little bit more in detail about those DC optimizers. So next slide, please. And inverters come in a few different flavors. There's micro inverters, which are basically designed to operate on a panel by panel basis. There's string level inverters, which are a little bit larger in size, which can take multiple strings anywhere from a couple kilowatts for a small residential system, all the way up to a couple hundred kilowatts for some of the industrial type settings. And then very large central inverters are mainly only used at those large scale utility plants. And what they do is they take that direct current from the panels, they optimize the DC to DC ratio of the voltage that comes through, and by operating a number of switches, can basically switch on and off how the voltage goes through the rest of the system to make it appear to be alternating as if it was what the grid sees. So, next slide, please. And when it comes to designing the overall system, there's a couple different ways to utilize inverters. So in what's known as a centralized conversion, you're utilizing all of your strings tied together and going into either one of those string inverters or into a utility scale, those central inverters, and that the shading or any of the effects that one string may have will carry through the entire system. But these are a lower cost way to build the system, and it's a lot simpler of a design. Whereas for the module integrated conversion, if you're using those microinverters, they're great for smaller systems, especially where if you think you may see some shading on individual panels, but they do increase the cost because you have to install an inverter with each panel. And as if one fails, you have to go up onto the roof to be able to repair those. So it's yet another one of those cost-benefit things that you have to take a look at when you're designing the system. And if you can go to the next slide, there's
David,
been
we need to wind down, please. Thank you.
Yeah, no problem. Like I mentioned, there's the DC-DC optimizers, which can kind of take some of those shading effects into account. So the next slide, basically the power that's coming goes from your house or that installation into the distribution grid, and that can provide some challenges. If you go to the next slide, with ensuring that we're trying to ensure we maintain reliability on the grid, as well as effectively take care of that any of the variability from cloud cover and weather and stuff like that. So those are some of the things that you'll potentially learn about in one of our later webinars about the research that our office is doing. And then next slide, I just wanted to quickly cover that solar plus storage is something you've probably heard about, and the main reason that it's coming up more and more is that the costs of batteries are dramatically reducing, and by adding storage to your solar system can allow you to use the energy that's harvested in the middle of the day, can use it later on when you come home, or help try to even out the generation throughout the day for a utility. And we've seen a lot of increases in residential systems and some non-residential systems throughout the years. And on an individual basis, there's definitely reasons to do that. And if you go to the next slide, one of the other things that our office is providing research on is integrating multiple solar and storage systems together through the use of smart controllers, so that we can utilize that energy to provide power to critical loads if there is like a hurricane event or a wildfire where that critical hospital or police department or fire department is isolated from the rest of the grid. We can utilize the solar and the storage to provide them long-term power solutions. And with that, Jonathan, I'll turn it over to you to introduce Kyle.
Great. Thank you very much, Dave. Really appreciate that informative presentation. And for all of you out there who have questions for David, please think of them and hold on to them. Again, we will take questions after the final presentation, which is coming up next. So we want you, while they're fresh in your mind, to take note of them and be able to ask David later. So thank you again, David. Really appreciate that. And now we're going to move on to our third and final speaker. And Kyle Fricker is a technology manager in the Department of Energy's solar office, working with the manufacturing and competitiveness and strategic analysis and institutional support teams. He manages a variety of projects, developing technology to streamline project development and financing, as well as facilitate grid interconnection and drive down lifetime costs of installed systems. His portfolio also includes projects that test, validate, and replicate new approaches to expand solar access to previously underserved populations. Kyle holds a BS in chemical engineering from the University of Florida and a PhD in earth and environmental engineering at Columbia University. And with that, we're very pleased to turn the floor over to Kyle. Kyle, over to you.
Thanks a lot, Jonathan. I'm excited to be here today. And in this section of the talk, we're going to zoom out of the technical components of the PV system and talk more at a higher level about some market trends and business models around going solar. You can advance to the next slide. So we got into this a little bit when discussing grid integration of solar previously, but I think it's really important to note that where you interconnect or integrate solar into the electric system has significant implications for the business model and operation of that asset. So on the left, we have the larger utility scale solar projects, which could cover land areas equivalent to hundreds of football fields each. And these systems integrate with the transmission grid and therefore fall under the regulatory jurisdiction of the Federal Energy Regulatory Commission, or the FERC. They employ numerous contractual arrangements depending on the financier and off-taker or electricity buyer, and also follow operational rules laid out by transmission market operators. Conversely, on the right-hand side of this figure, we have smaller scale distributed solar typically found on homes or businesses. The projects of this scale are located behind the meter from the utility's perspective, behind your electric meter. Distribution utilities set the rules at this scale, and many of them are regulated by state-level commissions. So we'll get into the behind-the-meter business model more in future slides. Let's keep going. And as you can see on this slide, and you may have seen driving through your neighborhood or the countryside lately, solar capacity has been increasing quite rapidly in recent years across all scales of solar projects. This was driven by a range of factors that we'll get into shortly, including policies and system cost reductions. So you can see on the left that the majority of market share by capacity is at the utility scale. So given the small kilowatt scale of residential PV systems, the actual number of those systems is quite astonishing. As you can see in the figure on the right, in 2019, we hit somewhere north of 2.2 million residential PV systems, which means that solar is on roughly 3% of single-family detached homes. Go to the next slide. And so you cannot really talk about energy in the United States and omit the role of policy, and solar is no exception. So over the years, many states have enacted renewable portfolio standards, which require that specified percentage of the electricity that utilities sell come from renewable resources. So to be clear, that we're not just talking about solar, all renewables. So states have created these standards to diversify their energy resources, promote domestic energy production, and encourage economic development. And an analysis out of one of our national labs, Berkeley National Lab, found that roughly half of the growth in U.S. renewable energy generation since the beginning of the 2000s can be attributed to these state-level renewable energy requirements. Policy impacts also occurred at the local level as well, with over 160 cities, 10 counties, and 8 states setting formal goals to power their communities with 100% renewable energy. So in total, that's over 100 million Americans now living in a community with an official 100% renewable electricity target. And last up on this slide is that it's not just governments that are setting these goals. There's over 250 RE100 companies that have made commitments to take their operations 100% renewable. Keep going to the next slide. And so the growth of the solar industry has brought with it many jobs, totaling nearly 250,000 jobs in the U.S. solar workforce in 2019, as tracked by the Solar Foundation, one of our awardees in their annual job census. As you can see, the majority of these jobs are in the installation and project development fields, but there are a wide variety of employment options within the sector. And from their research, I'd also like to point out that the solar wages they found are above national averages, with non-electrician mid-level employees receiving approximately $23 an hour, and electricians receiving $28 an hour. Next slide, please. And so looking a little bit closer at the growth of solar jobs over time, you can see a recent slowing down, and that's largely driven by some federal policy changes and also workforce efficiency improvements. Also, recently, some markets have decreased in employment, like California, Michigan, and Washington State, while we have seen increases in solar jobs in 31 states, such as Florida, Georgia, Utah, New York, and Texas. So that's really exciting. You can go to the next slide. I'm going to shift gears a bit and talk about the going solar process from first decision through to enjoying the benefits of solar, which most notably would be reducing your monthly electricity bill. So over the years, through aggressive goals, R&D programs, and industry collaborations, our office has played a role in transforming the going solar process. And I encourage those who are interested to dig into this a little more to follow the link on this slide for a really cool infographic that helps you visualize how some of our research and technology over the years has added clarity, speed, and cost savings to the going solar process. You can go to the next slide. So there's two main ownership models for residential solar. First is direct ownership, so via a cash purchase or debt financing via a loan. This approach is relatively straightforward and can result in a simpler transaction overall, but there are upfront capital or credit requirements that can limit the customer base. Second is third-party ownership, where the customer agrees to host the solar system and purchase the electricity from it. There's a trade-off in that the solar customer experiences low or no upfront costs, but they must share in the system benefits with the third party. So it's a bit of give and take. I'm not going to be able to get into all the details, but the diagram on the right shows the different parties and their relationship in that arrangement. And I'll draw your attention to the graphs below. So this is data tracked by Berkeley National Lab, which shows the growth and recent decline of third-party ownership in the residential segment, which reflects the emergence and proliferation of innovative residential loan products, as well as change in strategy from one of the leading providers. And also would note that on the non-residential side, there's actually been a bit of a flattening out, and that's due to the fact that a lot of tax-exempt sites, like nonprofits, churches, government buildings, et cetera, leverage the third-party ownership model to help them monetize tax benefits. So let's go to the next one, please. So regardless of the ownership model, the economics of going solar are driven by the underlying costs and benefits. So starting with the cost, the National Renewable Energy Lab helps us track every detail of solar system costs, from the clips that attach the panels to the racks, to the sales tax paid on those components, to the project development overhead, and everything in between. As you can see in the figure, the industry has seen cost declines of 70 to 80% since 2010. You could advance the slide a few more times. And back around then, the office set goals for 2020 that you can also see, as well as our progress as an industry towards achieving them. So a significant amount of the system cost decline is the result of reductions in the cost of equipment and materials that feed into these systems, as my colleagues have described very thoroughly. And many of those were achieved were driven by the economies of scale achieved in really scaling up solar manufacturing. We can advance to the next slide. So at the same time as the hardware cost declines, the soft costs have actually gone down as well, but just not by as much. So they now represent the majority of system costs, as shown in the graphic. So this represents a range of costs that are not the hardware, and also includes some barriers to deployment that some would call infinite soft costs, to really just prevent projects from getting done. You can go to the next slide. We'll dig into one of these in particular, the permitting, inspection, and interconnection costs. So these costs are essentially related to working with local decision makers to get the necessary approvals that you need in order to turn your solar system on, or get permission to operate, as it's called. And I would just point out that the Solar Office has funded and led numerous efforts over the years to drive down the times that these processes take, because longer time typically means more cost and more people, more customers potentially canceling along the way. And I would also point out that many jurisdictions and utilities are moving to online processes, and this movement has actually accelerated during the current pandemic. Current efforts are looking at how do we layer on storage into this equation, and how do we take learnings from going through this with solar alone and avoid the same pitfalls. We can continue on. And now shifting from costs onto benefits, wanted to briefly touch on the concept of net energy metering. So this is often referred to as net metering, but it's where a solar customer who is generating more electricity than they're consuming can export that excess electricity to the utility grid and receive a credit in kilowatt hours that can be applied to offset consumption of electricity within our current utility billing cycle, or often even future billing cycles as well. So it's a relatively simple compensation mechanism that's very easy for a utility to incorporate on top of their existing retail rates, but it's not without challenges, including that it may not accurately value the exported electricity, which has impacts on the utility business model. And that's why it's typically the mechanism of choice in new markets with low solar levels. And then as markets mature, they look towards more advanced valuation and compensation schemes like what is happening in California and New York currently.
Kyle, you need to wind down, please. Thank you.
Okay, let's go ahead and skip this slide. And this is just other financial benefits to going solar. I do want to briefly touch on a few new business models. So depending on who you ask, approximately 50% of individuals across the country cannot access rooftop solar for whatever reason. And these barriers tend to impact underserved communities, low-income communities, more than the rest. And so if we go to the next slide, one solution that has started to gain traction is called community solar. So that's a product where the financial benefits of a single solar system are distributed among an exclusive group of customers that have chosen to subscribe to the program. So think of it as like having a small piece of a larger solar system that's a 10-minute drive away from you, allocated to your utility bill. So DOE's efforts in this area are focusing on the challenges of applying these models to underserved communities where the economic benefits of solar can have a really tremendous impact. And then I think we'll move on to the next slide to just step briefly away from residential solar and talk about new business models involving land use and co-location of solar with both water reservoirs, so-called photovoltaics, and farming agrivoltaics. Won't read through all these benefits here, but there's a lot of synergies between these various co-locations, and current research in our office is looking to better understand and quantify the benefits of co-locating these types of systems. And I think the next two slides just touch on the fact that we always have positions open in our office, so please reach out to us if you would like more information on those. And particularly for the students on the line, we have fellowship programs that I would certainly like to direct your attention to, and they can be stepping stones between your university education and a full-time career down the road. So I think with that, we can wrap up.
Great. Thank you very much, Kyle. That was a really, really informative presentation, and lots to digest among the three presenters, lots of great information. And now is the time for you to be able to ask the questions that you have been thinking about as you've been listening to our speakers. Use the functionality on the screen to be able to chat in your question, or to click the button to virtually raise your hand, in which case you could be recognized. And now I'm going to turn things over to my colleague Tyler in about the 5 minutes that we have for questions before we have to close at the top of the hour. Tyler, over to you. Do we have any questions on the line?
We do. Thank you, Jonathan. First, we did receive several questions asking how attendees can access the recording. That will be posted online, information to be sent in an email to all attendees today. And in that same email will also be a link to the webinar recording itself. So no need to worry about that. As for the other questions, just diving right in here. Melody says that for Department of Defense projects, she is seeing a lot of issues with O&M staff maintaining PV panels, specifically regarding safety of accessing panels on roofs. And we actually got a couple other questions about maintaining panels, how important is maintaining roof access, the ease of accessing and making those repairs, et cetera. So I invite any and all of our panel members to weigh in on that question.
This is David. Just in terms of operations and maintenance in general, and when designing a system, it is definitely important to provide not just access for maintenance purposes for the panels, but also access for emergency responders in case there's fire or anything like that, because they do a lot of their operations on the roof as well for large buildings. So part of the code has been updated to make sure that there are standoffs between sections of the PV array, as well as access around the roof and through the middle and any of the other penetrations in the roof from like the HVAC and stuff like that. So those are definitely things to make sure that whoever's designing the placement of the system allows for all the code requirements and access not just for people, but for tools and laydown spaces as well.
Great, thank you very much. Another question for Dave. You mentioned integration into storage. Do you have any thoughts about battery chemistries and whether any work better than others with solar?
So there's a couple different offices within the department that are more focused on battery chemistry than others. I'll just say the lithium-ion chemistry has had a lot of research put into it because it's a very good chemistry for electric vehicles, and there's a large market for those second life batteries that are coming out of electric vehicles, which kind of dovetails well with solar. It all really depends on what you're trying to do. Those lithium-ion chemistries tend to be a lot more fast reacting. So if you're looking at small scale changes or short duration, like in the 4 to 6 hour range, they work great. But some of the flow battery technologies and other technologies out there are good for the longer term storage, which is really just like bulk storage, not necessarily running your system by changing the frequency response.
Excellent, thank you very much. I have a question from Eliza, who asks if any of you are aware of a comparative table where panel efficiency is documented by manufacturer and brand.
So there are a few resources that track cell and module efficiency. The National Renewable Energy Lab maintains a chart for cell efficiency. It's actually record cell efficiency, whereas the module efficiency is a more recent thing that they've begun adding. These are a little more geared towards records in terms of scientific achievements to show what panels, cells, and modules can do. The tables that compare modules tend to be actually a little more focused on reliability or other aspects of the modules, like the PV Evolution Labs, and puts out the module reliability scorecard that compares stress testing of different modules and how well the modules are able to hold up to different treatments, different kinds of conditions that would be very extreme in the field. In terms of efficiency, that information is usually kind of available online, and so it's usually known by people who are buying or selling a lot of modules. It can be useful to talk to an installer or to talk to a module acquisition specialist, and they'll probably have a list of what's out there.
Great, thank you very much. And looking at the clock, I just wanted to quickly note, because I got another follow-up question. If I didn't make it clear, I apologize. We will be sharing a recording of this webinar in a follow-up email that will be sent to all attendees. It will also be posted online in a link that will again be shared in that message. So I just want to make that clear once more. And I also we have a number of questions. Thanks everyone who joined us today for asking those. We are just about out of time, so I will share those questions with our panelists, and then they will be able to get in touch with you individually following today's call. And with that, I will turn it back over to you, Jonathan, to conclude this afternoon's presentation.
Great. Thank you very much, Tyler. And I want to say thank you very much again to our speakers. We are extremely grateful to Brian, David, and Kyle for sharing their sage wisdom from our Department of Energy's solar office. We value them greatly. They are a tremendous asset to the department and to our honestly, our country. And so we want to thank all of you as participants in the very first Solar Decathlon webinar. Please do join us in subsequent webinars each month through May, and share with your friends and family and colleagues, and we'll look forward to seeing you at the next one. This concludes our webinar for the day. Thank you, and have a great day. Take care.